Welcome back, class. This is Notes 15.3. This will be our last day of parametrics in Chapter 15. And I want to introduce a topic of collision and intersection with parametric graphs. So, just a quick reminder, when we use the word Cartesian graph, rectangular graph, they're really the same thing. So sometimes they'll ask for you to do something on a rectangular basis, some in the Cartesian, that still means the same thing. Next point, if we follow the path of two particles simultaneously, their paths may cross any number of times. The points of intersection are, of course, called intersecting points. Intersecting points that the particles occupy at the same time are called collision points. Example, in real life, we can imagine that as we go through a stop sign or intersection that has a stop sign, there are many paths that are going to cross and intersect throughout a particular day. Sometimes, though, there will be collisions, and that, of course, would be, in this example, when two cars meet at the same time at that intersection. So, paths crossing may or may not result in a collision or a collision point. So we have our first example, and our first example deals with two parametric curves. One, that the x-coordinate is based upon cosine of t, y is sine of t. The second curve is sine of t for x and cosine of t for y. I would like you to go ahead and graph these on your calculator. In doing this, you're going to have to go to parametric mode. And when you're in parametric mode, enter in the x-coordinate, the cosine of t, and the y-coordinate, sine of t, in the first graph. In your second graph, enter in sine of t for your x-coordinate and y of t for your cosine. Or excuse me, cosine of t for your y graph. This gives you a pretty easy one to graph. What I would also recommend is you go in and set your window. You'll see in this one that you'll have upper and lower for x and y. And I just set the screen up to look like -2 to 2 on the x's and -2 to 2 on the y's. Okay? Once you've graphed that, you'll see that it kind of fills in that graph. And also what you'll notice is that really we have two graphs at the same time. We have one graph that's going to go in this direction, and you probably noticed it took a moment and it filled in the graph and it went in a clockwise direction. And then you also notice that the other graph filled in and it was going in a counterclockwise direction. Now both of these have an infinite number of intersecting points. They're just repeating each other back and forth. But we want to find out where they will collide. Where they will collide, again, is called a collision point, and that's when they meet at the same point at the same time. In other words, we're at the same x values and the same y values. This one's rather easy to solve. We just substitute in our two x equations and our two y equations, setting those equal to each other. You may already look at it and say, I know when cosine and sine are the same, or you may just say, hey, let me divide both sides by cosine. That gives us tangent of t equals 1, and we know that tangent of t will equal each other at 1/4 pi and 1/5 of 5/4 of pi. We want to point back again at our domain. T is going from 0 to 2t, so that isn't an endless number of intersecting or collision points that we have. Okay? So that does answer the when the particles or when the two curves collide. occurs when t equals 1/4 pi and 5/4 of pi. The where is just a matter of going back in and substituting in these t values. The first one, t equals 1/4 of pi, we'll substitute that in. It doesn't matter which one we do because they should end up with the same amount. But if we substitute it in cosine, we'll get square root of 2 over 2. When we substitute 1/4 pi in the sine, we get the same value. So that's telling us that we have a collision point right here at square root of 2 divided by 2, comma, square root of 2 divided by 2. So that's one of our collision points here. And those would be the coordinates of that. And you'll see when we substitute in 5/4 of pi into those same equations, we get the second collision point, and that's over here. So these particles going in opposite directions collide. If there were particles moving along these curves, they would collide here and then here, one going in clockwise direction, one going in counterclockwise direction. Okay? So again, just a quick summary of what you're going to do with these is set your equations equal to each other, find out when the particles are at the same spot, and then if it's asking for where, then substitute those back into your equations. And also consider sometimes particles through the domain are going back and forth or repeat a path in some type of motion, and there may be more than one collision point. Next, I want to talk to you about the length of a curve, or it could be asked, what is the arc length? I want to look at this in three different ways. The first one is if, and this is the if, we have y is a function of x. In other words, f is dependent only on x. In that case, we are going to calculate the length of an arc, or excuse me, length of the curve, or arc length, by using the leftmost x value to the rightmost value in our integral. And you can see this kind of looks just like our distance formula, and it is based upon that. But in the second term, we have dy dx in here, and that is squared. Then we'll take the square root of that, integrate that with respect to x. In our other example, or other type, in this case, it's x that's dependent upon some function, and it's dependent on y alone. In that case, we're going to integrate from the bottom y value to the top y value. We'll take the square root of, in this case, it's going to be dx dy that we're going to take the derivative of, and then square that plus 1, and then that's with respect to y. Okay? Both of these are not parametric. Okay? It's something we've covered before in our non-parametric arc length equations. Okay? Now, the next situation is when we do have a parametric relationship. In other words, x and y are dependent upon another parameter. In those cases, we're going to integrate from our minimum t value to our maximum t value, and then it'll be the square root of dx dt squared plus dy dt squared. And we'll integrate that with respect to t. Okay? So let's do a couple examples of these. Our first one, or I'm sorry, a couple more points I want to point out to you as we go through these. The first one being that in order for us to do these calculations, we must have a smooth curve, and both derivatives must be continuous and not simultaneously zeros. Because in that case, when we do, that would mean typically that we don't have any cusp or any corners in there. Any of those will occur. Next point, point number 6, is our arc length formula only applies when this situation up here is true, when we do have that smooth curve. So point out to you that you need to check and make sure that it's smooth every time before you start your calculations. If it's not smooth, you're going to have to make an adjustment for that at the spot where something happens with that curve. Next, this formula will be used only if we transverse it once. We can't have a case where we're going right, left, right, left, right, left. With this, it won't take that into consideration. And that usually depends on the domain of t. So sometimes what we'll do is just adjust our t value, so we hit it once, and then if we repeat that 3 times, whatever our arc length is, if we're calculating, say, a total distance, then we'll multiply it by 3. But even though we're going back and forth, if it's just asking for the length of the arc, we only count one of those. We don't just keep going back and forth, and counting the same lengths over and over. Okay? So, and again, just to note to you guys that sometimes the wording will be, what is the distance traveled? And that would, of course, be just a matter of finding the length of that arc that the particle may have been traveling on. Okay? So let's take a look now at our examples here. We've got our first one, which has y equals this equation. And since this one is a non-parametric one, we want to quickly go over how we're going to set up this one on our calculator. For non-parametric, what you're going to do is put your equation in y1, then go to y2 and use your Math 8, the n-derive option. What you'll put in the parentheses, in the first set of parentheses, is that you're going to put y1. We want to take the derivative of y1, and then we'll do that with respect to x. Yeah? So in our first example here, this is what you'll basically put in your calculator. This same equation, and then in your y2, of course, like I've said over here, we'll put y1 in that Math 9. Okay? I do want to point out to you a quick note before you may make this mistake. Be careful entering this one. You usually find a few have a little problem in entering 1 divided by 2x. I want to point out to you 1 divided by 2x should not be entered in the calculator like this. This would be 1 divided by 2 times x, and that would, in other words, just be 1/2 times x. We want the 2x to be in the denominator, so make sure you do put that in parentheses. Okay, so let's go back, and again, hopefully by now you've put this in your y1. In your y2 we have this. To check whether we are smooth, we're only going to look at this first graph, so if you want to hide this one you can. It's no big deal if you don't hide that, but go with zoom 6 and you'll see that we have a curve that does appear, and you'll see as you kind of travel on that from, in this case we're going from 1/2 to 1 on our domain. So don't look at the whole graph on this one. We just want to look at the part of the graph where x is 1/2 to 1. And in that case, we should get a nice smooth graph, and we should be set. Also, you'll see as we go through this 1/2 to 1, there is no going back and forth, so to speak, on this one. Let me quickly just kind of show you what we have on that graph. Again, I've gone in and I've put my y1 and my y2 in the graph, and We need to turn these on and get a good graph of those. Another one set up already, and I want to go back to this one. So you'll see that's the original function, which does have an issue here at 0, but in our domain from 1/2 to 1, we are nice and smooth. And you'll see that we just travel this once. There is not a case here where we're going back and forth, obviously, because number one, this is not a parametric function that would cause us to go back and forth, back and forth. Okay? And again, I didn't turn off the derivative graph, but that's the shape of that one. Okay, so next thing we need to do is go ahead and find the length of this curve. Since the first two things have checked out okay, we can just go right to our calculator, enter in our function, which is going to look like one of these. Let me clear that out, and we'll go to our Math 9, and we'll integrate this from 1/2 to 1, and in here we'll do the square root of 1 plus our y var. We're going to go, I have that in y2. I'll enter that, and then be sure to square that and integrate this with respect to x. Enter, and we should get that value. So that is the length of this arc from 1/2 to 1. Let's take a look at our second one, and you'll see that this one is similar to our second example, or second type up above. In this case, x is the one that is dependent on y and y alone. So I went ahead and put those in my calculator already. You'll see I have y3 and y4 used up with those. And then now I'll go ahead and graph those. Maybe not. Got to turn them on first. There we go for the first one. I don't want to look at the derivative graph, so I'm just not going to highlight that one. Well, let's go ahead and watch this thing. And you'll see we have a domain from 0 to 1, 0 to 1, no problems. We should be good. And of course, just your knowledge of the graph should remind you that, hey, this shouldn't be a problem at all. And we are going to transverse this one time as we change those values. I do want to point out to you, you'll see that the calculator doesn't care if this is a y or an x. It's still going to do the same thing. So don't fret about the fact that our equation is x equals. We're just, again, evaluating the smoothness and whether it's transverse once or twice. Okay, let's go ahead and go to our calculation. So again, we're going to, I think I have this in here somewhere else. There it is. You'll see I had to use y4 because I had the other equations already in y1 and y2. So my equation this time was in y3 and y4. y4 is the derivative of the function, integrating it from 0 to 1. And we should get 1.4397 for our the length of that arc. Okay, let's take a look at our next example. And in our next example, we have this time parametric equations. Our first one, our x equation, is e to the t times cosine of t. Our second equation is y equals e to the t times sine of t. Our domain is from 0 to pi. So we will, this time, go into your calculator and press mode. And we're going to go to parametric. Once we have a graph or calculator in parametric mode. When we go to y equal, you can see I've already set these up in my x1, y1, and also what you're going to want to do is go to your x2, y2 and put those derivatives in there. Once again, when you go to these, I'll repeat this one real quickly for you. You're going to go to math, and our derivative is 8x, and then we're going to go to our vars, and our y vars, we're not under function anymore, we're under parametric. So go to parametric and enter in x1 for this one, and of course y1 for the next one. That goes in here, and then we integrate this with respect, or excuse me, take the derivative with respect to t. And likewise, you'll do the same thing for your y2 value. Okay? So now that I have those in there, I do want to go back and turn this graph off and go ahead and typically a zoom 6 is what I just start out with, and take a look at it. And you'll see that this one quickly graphed itself, and it went in a smooth way from here on, and it's going to graph itself from t equals 0 and to pi. There is no problems of going back and forth on this one over that domain. So we are smooth, we travel at once, therefore our equation is going to work. So in our calculator, what we're going to do is, and again I have that entered in here somewhere, there it is. You'll see I'm integrating this from 0 to pi. Then we'll take the square root, and then just like we did before, you're going to go to your vars and choose, oops, did not want to do that one, vars, and go to parametric, and then choose your x and y respectively for this one. Since we're looking at the derivatives, my derivatives are in x2 and y2, so that's why you see the x2 and the y2 being squared underneath the radical. Calculator is going to do the rest. All I have to do is press enter, and you'll see we get a value of 31.311 as the length of that arc from 0 to pi. Let's take a look at our next equation. And our next equation, we're going to go ahead and do this one without a calculator. That is something that you'll be expected to do. Some of these will be with calculator, some without a calculator. Obviously without a calculator, the derivatives and the integrals should be a little bit simpler than without. But you'll see the first thing I did is just went ahead and take the derivative, being sure to make sure I don't miss the chain rule. Derivative of the inside is 3 times 3. And the same thing over here. So the two derivatives of our x and y functions are given to us. And also, I need to think about this as being smooth. And over this domain, I know that my sine and cosine curves don't have any issues with any corners or cusps or any jumps in those. So I know that I am smooth. But I do want to note on this one, think about this. We know this shape because we've kind of seen this shape, but regardless of knowing about that shape, we know that something's going on here that's going to keep repeating itself. We're going to get the exact same values several times on this one because we know sine and cosine repeat their values, and that's going to occur because the t on the inside is tripled. So yes, we're going from 0 to 2 pi with t, but the cosine is going to see this from 0 to 6 pi. Sine is going to see this from 0 to 6 pi. So we know that that's going to triple the amount of times that this thing is going to repeat itself. So another way of looking at this is saying I know that we have a 0 to 2 pi period in the sine and cosine curves. So if x is 3t, then we know when I divide everything by 3 here, I have from 0 to 2/3 of pi, I will have this sine graph and cosine graph go through and do one of its periods. And then that same graph is going to repeat from 2/3 pi to 4/3 pi. And then again, from 4/3 pi to the end of our domain, 2 pi. Okay? So in this case, what that tells me is if I do this from 0 to 2 pi, I'm going to have 3 times the length that I want. So I could find that and then divide that by 3, or better yet, let's just do one of the periods, and that's from 0 to 2/3 of pi. Now I ran out of room, so let's take a look at what I'm doing here. Again, this one is a no calculator. If it were a calculator, put it in the calculator, let the calculator do what it did the last time. But in this case, we have our x prime and y prime values substituted in. Those quantities get squared. Also note again, we're going from 0 to 2/3 pi. I just square those, get 81 cosine squared of 3t plus 81 sine squared of 3t. Factor out the 81, and we'll have inside of our parentheses, we'll have cosine squared of 3t plus sine squared of 3t. Now, the 3t is not going to bother me here because I know that cosine squared of anything plus sine squared of that same thing is always going to be equal to 1, which means we're just going to do the integral from 0 to 2/3 pi of the square root of 81, which of course is just 9. When we integrate that, we get 9t, and we're going to evaluate this from 0 to 2/3 pi. The 0 is nice and easy. Of course, we have 2/3 times 9, which ends up giving us an arc length of 6 pi for this one. Next, I want to point out a quick little note to you. Be careful on these questions. Sometimes they'll say, they'll word it this way. We'll say, what is the distance the particle is from its initial position? And sometimes they'll say, what is the distance the particle has traveled during the path? Those may not be the exact same thing. The distance from its initial position to its current position is just a straight line from x1, y1 to x2, y2. That's how far it is away from its initial position, which would be just a distance formula problem. That wouldn't be the same if the particle took any other path rather than that straight line distance. If it takes another path, you can see that in this case we'll want to do our arc length calculation, not the distance formula. Okay? Next topic I want to talk to you about is the idea of speed. And first of all, let's look at it on a horizontal line or a vertical line. Our speed is just going to be the absolute value of our velocity function. So, a quick little example here. You can see that we're traveling along, and our distance is based upon t squared minus 3t. So, our velocity function is just a simple derivative, 2t minus 3. So the speed when the particle is at 1, we just substitute in 1 into our velocity function, making sure that we take the absolute value of that, and we get a speed of 1. Pretty straightforward and simple for us to do. Okay. Next, let's take a look at that same idea, but now what if I have a parametric curve? Well, it's still denoted by absolute value of v of t is our speed. But this time, in order to do that, we're going to have to take the square root of dx dt squared plus dy dt squared. Again, it's kind of that distance formula relationship that keeps applying in this. And so we've got a few examples to do for these, starting off with the first one, where we have two functions. X is a function of sine of t, y is the function of 2 cosine of t, and we're going to see what is the speed of this object when t equals 1/4. Derivative of x, derivative of y, gives us those two functions. Next, we'll write our speed function by doing x prime squared plus y prime squared, and then the square root of that. Then substitute in our 1/4 of pi, cosine of 1/4 pi, sine of 1/4 pi, multiply inside, which just gives us square root of 2, which is squared, negative square root of 2 squared, which is also 2. 2 plus 2 is 4. Square root is 2. So the speed of the particle on this curve would be 2. Let's take a look at our second one. In this one, x is a function of, actually a linear function of t, 2 minus t. Y equals the square root of t. Two simple derivatives that we take. And again, we're going to take those and substitute those into our general equation. First part is rather simple there. We're just square rooting -1 regardless of the value of t. But the second one, or second part of this, we'll substitute in 1. Square root of that is 1 times 1/2. Square that and we get 1/4. 1/4 plus 1 is 5/4. The square root of this would give us the square root of 5 divided by 2, and that is the speed of our particle when t equals 1. Now, let's take a look at our next problem. And our next problem, you'll see, is an extended response problem that I'd like for you. Well, first of all, it is a calculator permitted. There is one part of this that we are going to skip. We haven't covered acceleration vectors yet, but I would like you to go ahead and pause this video and go ahead and try this on your own. This is one that does use some of the same things we've just done, and I think this is a good one for you to try. So I'm just going to pause a second so you can pause your video and go ahead and try this problem. Okay. Hopefully you've tried this, and welcome back. Let's go ahead and walk ourselves through this one. You'll see that we have a parametric curve as it's kind of defined here. Do we know what x of t is? No. Do we know what y of t is? No. But we do know at time t equals 2, we are at 1/5. We only have positive t values in this case, and they only give us our first derivatives. Original function is not given to us. So first question is the horizontal movement of the particle to the left or to the right at t equals 2? Explain your answers. And it says find the slope of the path of the curve at t equals 2. So let's think about this. Horizontal movement doesn't care what we're doing up and down. It's just going to move right or left based upon dx dt. So we know that we will be going left if dx dt is less than 0. We're going to be going right if dx dt is greater than 0. So this one actually is just a matter of simple algebra, substituting in 2 in the equation that they gave us and checking to see that 2 divided by e squared is greater than 0. Therefore, the movement is to the right, since dx dt at t equals 2 is greater than 0. Boom. That explains our answer, and it gets this. Now, be careful. When you look at the scores of the students who did this, there were a significant number who didn't read the full question, or maybe read it, got busy doing the first part, and then forgot the second part. So that is one thing that does appear every once in a while on the AP type questions, where there is a second calculation in part A that's not broken out to say, oh, this is A and this is B. So be very careful. Make sure that you don't forget that second part. And the second part is relatively easy, because we're going to remember that our slope is just y prime divided by x prime. So y prime equation is given to us, x prime equation is given to us. We just now need to evaluate that. Since this was calculator permitted, I didn't worry about anything else. I just put that in my calculator with the value of 2 for t, and that gave me the value of 3.054. Boom. We are done with part A. Next, part B says, let's find the x-coordinate of the particle's position at time t equals 4. Again, this is only the x. What we're doing up and down doesn't matter. It's just saying where we are in the x direction. So you'll see that Alexis reminded us, hey, wait a second, this sounds like an end equals a start plus net change, and we thank her for doing that. And that helps us see exactly where to solve this one, because in the very beginning it told us that at x equals, or excuse me, at t equals 2, x would be at and have the value of 1. And we're looking at this for when t equals 4. So we'll integrate this from 2 to 4. We have our dx dt given to us. And we're trying to find out what that value is when x is 4. I went ahead and put this in my calculator, got that value, and then all I have to do is just add 1 to that. 1 was, again, our initial condition, and we end up with this as the x-coordinate only when time t equals 4. The next one says, let's find the speed of the particle at t equals 4. Again, the acceleration vector is something we haven't done, but this is right out of our notes from today. Our speed, the square root of dx dt squared plus dy dt squared. Just go ahead and put that in your calculator using 4 for your value of t. So that should be a 4 here. Sorry about that. Because t equals 4, substitute those values in, and our calculator should give us 0.574. Our last part of this one is, again, just right out of our notes today, the distance traveled by the particle. Okay. Now again, I do want to point out to you a particle is moving along a curve, so at any position it's given by this. So we must assume that it is a nice smooth curve based upon we have x and y values. There's no limitations to that. We're not going to be repeating any of this. So our calculation strictly is just going to be the integral from 0 to 4 of the square root of our dx dt squared plus our dy dt squared, which rather than repeat writing those down again, I just put those as this to get my point there, and then calculated this to be 0.650. Okay. Real quickly, I do want to just go over the scoring on this one, just so you're familiar again as we prepare for the AP exam, what they'll be grading this upon. So you'll see The very first one was simply a matter of answering the question correctly, moving to the right with a reason. So we'd have to show that we did get a positive value, and then note that we got a positive value for dx dt, therefore we're moving to the right. Then that find the slope of the path of the particle at time t equals 2, that's actually worth 2 points. First was just setting up the fact that we're going to have a sine squared of t divided by the square root of t plus 2 divided by e to the t, which would be this calculation, and that would give us the value we have there. So 2 points for that one. The next one, you'll see that this one is also a 2-point problem. One for writing the integral. So just a word to those 4 guys in the class who choose not to write everything down. You'll see that you would have only gotten half credit for this just by writing the 1.252. So make sure again you're showing the grader what in the world you're doing. So just writing our integral gives us 1 point. Next one was just a 2-point, calculating the speed correctly, and we didn't do the acceleration vector. We'll do that a little bit later this unit. And then finally, the last part of this is that we have shown again our work by putting the integral down and done our calculation. So that concludes today's lesson and concludes our look at parametric equations. Hopefully you'll work through these problems rather easily. We'll look at 15.4 on the next video.